Swayam Prabha. Digital India. Educated India.
Hi, I am Dr. Raj Shekhar. I am a faculty member at the Department of Architecture and Planning, Indian Institute of Technology, Roorkee. As a part of NPTEL, I am offering a course titled Principles and Applications of Building Science. This is a 10-hour course. For your ease of learning, we have split the course into 20 different modules. Each module lasts for about half an hour. This particular course deals primarily with the physics of the building. Today, as you know, energy efficiency, functional performance of building, energy conscious design, climate responsive architecture, these kind of buzzwords have been much in the industry. Every particular building, every designer is aspiring to do a climate responsive, energy efficient, green, so called green buildings. This course would train you hands on, it will give you information about how do we do energy conscious, functionally efficient building design. When I say functional efficiency, there are three main components. First is the thermal performance of building. Second is how do you design your acoustics in your building, acoustics and noise control, and third is the lighting design. Specifically, these three things are going to be covered. We will have 4 weeks in which the course is offered. The first part of the course, that is the first week, we will start with solar geometry and climate classifications, the basis of climate classifications. We will talk about thermal comfort, thermal adaptation, some formulas, how are things quantified. Then we will talk about bioclimatic assessment, what are the passive design strategies which works in a climate, which will not work in a climate, both qualitatively as well as quantitatively. Then we will look at building envelopes in detail, thermal performance of building envelopes. We will study more in detail about glass and glazing systems. I will teach you about shading analysis. In this process, I will be teaching you or using certain tools, softwares, I will be demonstrating you these tools, and some of these tools I will be giving exercises on. Each week you will have specific assignments. I will be asking you either numerically or as a essay type, you will have to write and submit it to me for evaluation. The third week we will start with acoustical design, environmental acoustics and noise control design, what are the quality indicators as far acoustical design is concerned, and the last spell of the course we will talk about daylighting, basics of lighting as well as daylight harvesting in buildings. So I will be using, as I said, certain software tools which I will be demonstrating. Some of them I will expect you to work hands on and submit me in the form of exercises. This course will be highly beneficial for the students of architecture, students of civil and mechanical engineering, apart from practicing architects who wish to brush up their basics in building physics and building science. There are no specific prerequisites for this course, but basic knowledge of Microsoft Office like Excel, Word, PowerPoint would be useful if you have to work on certain assignments. Apart from this softwares, I will be demonstrating you, so specific prerequisites are not mandatory. For those who are interested in taking a certificate, at the end of the course there would be an online examination. You can appear for it. I am looking forward to seeing you in the course. Thank you. Welcome to the course Principles and Applications of Building Science. This is the first module. Here we will start with solar geometry. Mainly we will talk about earth sun relationship, sun path diagrams, and what is the consequence of it on the solar time and local time, how they are different. Solar radiation, specifically we will look at how to measure and what are its implications. Finally we will look at how does that affect building design, what are the design implications. To start with, we will look at earth sun relationship. Some of this we already know. We will relate it more with climatic building design. The climate of earth, as you know, is driven by the energy input from the sun. Sun is a source of energy. There are two essential aspects that a person has to understand. One is the apparent movement of the sun, or if you take a geocentric theory, it is apparent movement of the sun, where the sun's position is, that is a solar geometry we typically refer as. And number two is the energy flow from the sun, be it heat energy, be it light energy, it is energy flow from sun to the earth, and how to handle it, whether you will include it in the building or exclude it in the building. So two primary things, one is the solar geometry, number two is the energy flows associated with it. Considering a heliocentric view, you have sun in the center, earth is moving around at 365 days, the axis which is subtended with the equatorial plane and the sun, this particular angle, the tilt of earth is 23.5 degrees, this is constant tilt. As the earth moves around, you start getting two typical extremes. One is called northern solstice, that is when 23.5 degrees plus, that is on June 21st and 22nd it happens, that is the day times are maximum, the night times are minimum in the northern hemisphere. Typically we call northern solstice. For countries or locations in northern hemisphere, this is called summer solstice. On the other side, winter solstice or the southern solstice for northern hemisphere, which occurs on December 22nd, that is minus 23.5 degree tilt. Typically this is referred as southern solstice. For locations in northern hemisphere, we refer to this as winter solstice. This is where you get the shortest day and longest night. Typically we get minimum temperatures in this particular season. Apart from this, when earth is typically there is a 0 degree tilt, you call it as equinox. It occurs twice, that is March, 3rd week of March and 3rd week of September. So there are 4 important dates which are critical if we have to understand solar geometry. First is northern solstice or summer solstice for northern hemisphere. Next is 2 equinoxes which occurs in March and September, and the last one is winter solstice or southern solstice which occurs, which typically is a minimum temperatures associated with northern hemisphere. It is exactly the opposite for southern hemisphere. So during northern solstice they have winters and during southern solstice they have their summers. So we have equator here, Tropic of Cancer and Tropic of Capricorn, 23.5 degrees north, 0 degrees and 23.5 degrees south. So we are talking primarily about India or Asian part. So primarily we will look at what happens around here and what is the impact of the solar geometry on this our particular location. So if we have to understand more, or if we have to derive some implications of the solar geometry on our design, we have to start mapping the sun position. The first step is to get into a lococentric theory and get 2 typical angles to map the sun's position on a 2-dimensional plane. Sun is a 3D moving. So from that you are deriving 2 typical angles from which you can project. It is a trigonometric projection. First thing is the altitude angle. Whichever orientation it is, you typically take a horizontal plane and you mark the position of the sun. The angle which is subtended to the horizontal plane is called altitude angle. Higher the altitude angle, sun is towards your head, that is 90 degree means sun is just above your head. Typically if you say east and west, you get very low altitude angles. Next is azimuth angle, which you can take either north or south as reference. Many cases you take north as a reference, and wherever the sun's position is, irrespective of its altitude angle where it is located, you typically project it down and take the angle difference between or the angle subtended from north. For example, when sun is right on the eastern side, you can say it is 90 degree, or towards the west it will be 270 degrees if you are taking north as a reference point. If you have to really calculate altitude angle and azimuth angle, these are trigonometric calculations. So you need few indicators like declination, which we talked about earlier. You need the hour angle from solar noon, then you will need the number of day of year. So with these things there are some formulas we are not going to work out as a part of this module, but if somebody is interested, these are, if you know these 3 to 4 numbers, it is easier to locate the position of the sun, it is easy to calculate altitude and azimuth angles. We will go more with a graphical representation given the shorter duration of these specific modules. Let us consider 2 specific examples to get a better picture of these solar movements. First let us take a location Srinagar, typically northern part of India. The latitude is 34.1 degree north and longitude is 74.8 degree east. First let us look at what is the impact of change in latitude. So we will be considering Srinagar first, followed by Trivandrum, which is in the southern tip of India. So first next we will look at longitude, where we will talk about the solar time, how to calculate derive local time from that. So we will look at that. First let us take a look at the latitude of the place, 34 degree north. There are 3 images. This is summer solstice, where you have, here we are referring to the northern solstice or summer solstice here. Sun's position, it rises somewhere, then at this point, then it moves, traverses, sets here. Typically you get sun right above the head, this is on summer solstice. It never crosses towards the northern side, it is slightly tilted towards south, but still you get sun from the northeast and northwestern side during the morning and evening times. During equinox, if you see, sun moves, the sun rises here, moves along and then sets in this point. So typically you get sun rising exactly in the east, setting exactly in the west during equinox, but it traverses it has a southern traverse, it rises in the east, traverses through south and sets in the west. Winter solstice, you have further lower altitude angle. Here we are talking about 3 altitude angles. This altitude angle is high, slightly lesser, and winter solstice December 21st, here we have typically the least possible altitude angle. You do not get sun directly on the east or the west, it is mostly somewhere close to southeast and southwest, and it has a southern traverse. This is the case of 34 degree north latitude. Take a look at Trivandrum, this is 8.5 degrees north latitude, much closer to equator. So when we looked at Srinagar, it is off Tropic of Cancer, it is further north of Tropic of Cancer. Here we are talking about a location south of Tropic of Cancer, much closer to the equator. If you look at the sun movement, it has, the sunrise happens somewhere close to northeast, sets somewhere close to northwest. It traverses not directly through south, it is somewhat off the center point, that is, it has a slightly northern traverse during summer solstice, it is further off. So this is a center point, this is south, this part is north, so it has a typical northern traverse. What implication this has? If you have a northern wall which has large windows, typically during summer, especially in latitudes like this, say 11 degrees, 10 degrees or even 15 degrees, 13 degrees north latitude, you will have solar incidence on your northern facade and northern windows during summer months. The lower you go towards equator, like typically the case of 8 degrees, 8.5 degrees north latitude, you will have up to 4.5 months you will have solar incidence on your northern wall. So when you are blindly following a code which says, or a textbook which says sun traverses from east to west through south, northern wall or northern facades are free of direct solar radiation, it might be misleading. You have to closely look at what latitude it is which decides, because critical months like summers like May, June, July, where solar radiation is also more, temperatures are also more, you are going to get direct solar radiation on your northern facade here. During equinox, east and west, a slight southern traverse is noted, it is slightly off the center point, slightly traverses towards the south. Winter solstice, the altitude angle if you compare with Srinagar is not as low as you looked at Srinagar, you do not get such a low steep penetration of solar radiation, it is slightly higher in terms of altitude angle. In all the 3 cases, the altitude angle is much higher compared to 34 degrees, that is the location Srinagar which we talked about. Now let us look at something called sun path diagram, which is highly useful if you are designing a building specifically for shading devices or locating, orienting your building. For anything to start with, sun path diagram is a basic requirement. It is nothing but a projection, a 2-dimensional projection of a 3D movement. Mostly we refer to stereographic projection. There are other types like orthographic, we will look at few of them, just for an example. Primarily we are working with a stereographic projection. There are other things, as I said, like spherical, orthographic, but mainly we are looking at a stereographic projection. You need 2 specific angles, that is altitude angle and azimuth angle, to locate or map the position of the sun. Now coming back to our 2 example cities, Srinagar and Trivandrum, the solar movement can be mapped like this. We looked at in the 3 dimension. Now this is what we were talking about. This is your traverse of sun during your summer solstice, this is your traverse of sun during winter solstice. Equinox occurs somewhere here. We will look at the components more in detail. This is for Trivandrum, like I said, this is a center point, these are month lines. So if you see up to 4 months easily you will get direct solar radiation or solar incidence on northern facade. If you have to assess a northern facade will fall somewhere in this center line. Again southern facade you have to take this as a center line and see how many months or how much duration you have solar incidence on your southern facade. So typically in this case your northern facade is going to have solar incidence for more duration, whereas here it is only for 2 to 3 months, that too slightly in the mornings and evenings, which can be prevented or obstructed through a vertical shading system. Here you will also need a horizontal shade on your northern wall in order to avoid direct solar radiation during summer. In laboratories this particular thing is studied using heliodon. You might have heard of this name. This is a device where you can set the solar position, everything is adjustable, you can set latitude, longitude, solar position. Then typically these are lights which cast shadows. You can put your model and you can assess what is the shadow of penetration, what is the solar incidence. These things can be experimentally assessed. In this module we are going to look at, this is a graphic, 3D graphic which is generated by a software called Ecotect. We will be primarily using for demonstrations, we will be using the models from Ecotect as well as associated tool called Solar Tool, which helps us to graphically represent a 3-dimensional sun path. So similar thing which we are going to look at. This is a solar tool which I was talking about. Here we are talking about the solar path. This is a stereographic projection. There are different types of projections, as I said, spherical, equidistant, stereographic, orthographic, wall ramps. You can also look at tabular mapping of it. There are key components here. The peripheral line represents the azimuthal angle which we talked about. Then the concentric line talks about altitude angle. These are the date lines, month lines, summer to winter solstice, and these things are the hour lines. So knowing these date and hour lines, you can locate the sun's position at a particular point. Other than this, this particular tool lets you set the date and time. Say for example, if you are setting June 21st, then you will have summer solstice here. For a particular time you will know where the sun's position is. When you change it to winter, that is December, sun position changes here. You can also change the latitude of the place. Simply now it is 34 degrees, that is for Srinagar. If I change it to Trivandrum's location, the solar path, that is a total sun path diagram varies. This is during December and this is during June. A simple representation of sun movement. We will look at the shadow and shadow assessments further in detail. So far we have been dealing with the latitude of a location and how it affects the sun's movement. Now in this section we will talk about the impact of longitude and primary considerations which we have to give. So for this, one major thing we have to understand is the difference between solar time and the local time. The time used in the solar chart is a general solar time. It coincides with the local clock time only at a reference longitude for a particular time zone. Say if you take the case of India, we do not have different time zones. There is one time zone across the country, though we have a vast extent from west to the east. We have only single time zone. The reference longitude for India is 82.3 degrees east longitude. If you take a country like US, they have a different time zones. As you go from east to west of United States, the time zone varies. For example, they have half an hour to 1 hour time adjustment every time zone as you move from east to west. For a basic understanding, every degree of longitude you move, it means a time difference of 4 minutes. We will use this in further calculations. To understand this better, let us consider two locations. First is Mumbai, which is 73 degrees east longitude on the western side of India. Number 2 is Dibrugarh, which is 95 degrees east longitude, which is farther east of India. Mumbai lies west of India's reference longitude, that is 82 degrees reference line. It lies west of reference line by 9.5 or 9 degrees 30 minutes, whereas Dibrugarh lies on the east of India's reference longitude by 12 degrees and 30 minutes. Another thing which has to be factored in the calculation is the equation of time correction. It can be done, like I said earlier, it can be done numerically, but I am showing you a graphic indicator, the simple graph which tells you how to find out the correction, time correction. This has, along the x axis, it has a number of day, that is day of the year, start from 0, it goes to 365, 366. Then on the y axis we have the equation of time correction. This depends on the day of the year considered. For example, if you take 26th January, it comes somewhere here, 26th day of the year, the time correction will be minus 13 minutes. If you take 26th October or 27th October, which is somewhere around the 300th day of the year, the time correction will be plus 17 minutes. Using this, what we can do, if you take the same case of Mumbai and Dibrugarh, the calculation goes like this. Say for example, if I have to establish what is a local solar noon, what time the local noon occurs in Mumbai. Noon is 12 o'clock minus 38 minutes. This 38 comes from this 9 degree 30 minutes. If you multiply that for every longitude degree, it is 4 minutes. So if you multiply, you will get 38 minutes minus 13, because I am calculating it for 26th January. Whereas if I am calculating it for, say as an example I stated 26th October or 27th October, the correction will be in positive, it will be plus say 17 minutes. Here it is minus 13. So this comes to 11 9. Subtract this from 12. So you will get 51 minutes. So local solar noon at Mumbai occurs 51 minutes later than Indian Standard Time, because it lies to the west of the reference longitude. In the case of Dibrugarh, the same way if we calculate, we find that the local solar noon occurs 37 minutes earlier than the Indian Standard Time. If India were to have different time zones from east to west, then the time zone adjustments will be something like half an hour to 45 minutes for each time zone, if one were to divide the country into 3 different time zones. We will look little bit more in detail about solar radiation. 2 main measures are there. Number 1 is irradiance, watts per meter square, most commonly used. It is an instantaneous flux or energy flow. Earlier it used to be called solar intensity, it is now called irradiance, watts per square meter. It can be horizontal, it can be vertical. And number 2 is irradiation, which means the energy quantity integrated over a specific time. It can be per day, per hour, or per year total, or for a specific season. It is measured in watt hour per meter square. Looking little bit more into the details of solar radiation itself, the sun's surface is around 6000 degrees centigrade. Peak of its radiation emission occurs at 550 nanometer wavelength. So this is a solar spectrum. We know 3 major things. One is a visible spectrum, then you have ultraviolet and infrared. Once the sun's energy hits Earth's atmosphere, part of it is reflected back, part of it is absorbed, part of it is transmitted. Whatever component is absorbed is re-radiated. Then after entering the Earth's atmosphere, the ground absorption or water bodies, they absorb part of it, they reflect part of it. Whatever is absorbed is re-emitted. What comes in as short wave radiation. Once it is absorbed and then re-radiated, it goes back as long wave radiation. These long wave radiations are trapped by the cloud cover, which we generally call greenhouse effect, where this re-radiated long wave radiation gets trapped in the Earth's atmosphere. There is a large variation in irradiation among different locations of the Earth. This is for 3 main reasons. One is the angle of incidence. We know the cosine law, which states that the steeper the angle of incidence, the difference will be more. Number 2 is the atmospheric depletion. Again, it is a factor of the angle of incidence. For example, if it is in the polar region, the same sun's radiation have to traverse a long distance across the atmosphere, cutting through. So there is a factor which varies between 0.2 and 0.7. Then number 3 is the duration of sunshine. For example, earlier we said summer solstice versus winter solstice, or the northern solstice versus southern solstice, where the sun's duration of sunshine considerably varies between June 21st and December 22nd. So this has a considerable impact on the irradiation. Let us come back to the example of Srinagar, which is 34 degrees north and 74.8 degrees east longitude. You take the same southern wall surface. I put some windows and some shading systems here. If you take the solar radiation incidence on a winter, this is winter solstice, you have a steep southern sun. This is where the solar radiation incidence occurs. If you see in this scale, this portion corresponds to somewhere around 3000 watt hours. This is for a particular day. On the instance of December 22nd, this is what is the solar radiation which occurs on the southern surface. This is a total solar radiation. One more thing we have to remember is this total solar radiation has 2 components. One is a direct radiation, another is a diffuse radiation. For example, consider this surface at this point of time, this is around noon. This particular surface is not getting any direct solar radiation, but still the radiation will be there because of diffuse components. Diffuse radiation will still have some impact on these surfaces. Total radiation, net radiation will be minimum, lesser. Consider the case of Trivandrum, which is 8.5 degrees north latitude. This is again winter solstice. The southern sun is not as steep as you found in Srinagar, it is slightly with a higher altitude angle. Carefully look at this numbers, the total solar radiation incident on a southern facade, which is somewhere around 6000 watt hours. So, the solar incidence you receive on the southern facade considerably varies between the northern part of India, that is a location like Srinagar versus Trivandrum. Now let us not worry about what climate condition it is. Srinagar has a colder climate versus Trivandrum has a warm and humid climate. Now we are not getting into the climate classification, that is part of a different module, the subsequent modules, but just the solar radiation intensity considerably varies on a given building facade. How do we account for this particular solar radiation in our building related calculation? The main parameter which is used is soil air temperature. Soil air temperature is kind of a inclusive number, which if you read this equation, this is T out is a outside air temperature in degree centigrade. This is a drivable temperature of outside air. Soil air temperature actually includes the effect of air temperature and adds up a small component to it, which is inclusive of the main thing, global solar irradiance watts per meter square, absorptivity of a particular surface. So say imagine the same southern facade which I was talking about, if it were to be bright colored, say a white surface versus a black surface, the absorptivity of the surface considerably varies. So in that case this particular factor will vary. The third part of this small factor is H naught, or the heat transfer coefficient for radiation and convection. This is equivalent to the film coefficient on the outside surface of the wall. So this particular factor is added to the outside air temperature. So soil air temperature typically will be equal or more than the ambient air temperature in tropical climates. What happens is, say imagine if you take a western facade somewhere around 4 o'clock in the evening, there will be an ambient temperature. Take a case like Srinagar in June 21st, say the ambient temperature is 30 degrees, the southern facade which we looked at, the solar radiation intensity will be X plus the absorptivity of a surface, imagine a white surface, there will be a heat transfer coefficient. So a small magnitude, say about 4 to 5 degrees will get added up, which becomes the soil air temperature. This is more or less equivalent to the surface temperature of a particular wall. I have done some calculations using the same equation. Take this location, this dotted line represents the outside air temperature, starts from 6 o'clock, this is evening 6, this is a 12-hour graph. Morning the temperatures are around 27 degree and goes up to 35 degree in the evening. There are two other lines in this graph, this is time in hours, this is temperature. There are two other lines, this is soil air temperature on the eastern facade, this blue line, versus this purple line, this is a soil air temperature on the western facade. Interestingly, if you notice, the eastern facade, the soil air temperature goes as high as 40 degrees early in the morning only, around say 7 to 9 o'clock the peak occurs, then it cools down, comes back below the ambient air temperature. Whereas on a western facade, the soil air temperature rise much lower than the ambient temperature, and then it picks up in the evening and then it gets heated up. What is the impact on building design? For example, if you have to have a wall which is part of a bedroom, your bedroom wall is exposed to eastern side, the soil air temperature will go as high as 40 degree in the morning, then it will cool down. So when you want to occupy it somewhere around 9 o'clock in the night, the surface temperature is not that high, so including the time lag which we will discuss later, the inside temperatures will be relatively cooler. Whereas a west facing wall of a bedroom, the maximum temperature occurs somewhere around 4 o'clock to 5 o'clock in the evening, then this will be transmitted in, so you will have relatively higher temperature, inside surface temperature as well as heat gain through that particular wall. Here we did a small calculation. As such, soil air temperature is dependent on two main things. One, we earlier saw the absorptivity of a surface, that is represented by A. for a brighter surface versus a reflective surface versus a darker surface. Number 2 is it can be modified with the effect of shading. What happens in the case of shading? Moment you have a shading device or a balcony, the direct solar radiation is cut, but you have to keep in mind the diffuse solar radiation still exists, so it is not totally negated, but the direct component, which is quite significant, is totally negated if you have a full cover of shading. We have calculated the solar temperature ranges for 8 orientations. There are 3 cases here. The first case, this is a dark blue, the absorption, the solar absorptions of the surface is 0.4, which corresponds to a normal white painted or a ivory color painted external wall. There is direct solar radiation, it does not have any shading. Number 2, this light blue, where we painted the surface with a reflective coating. Today we get a lot of reflective, commonly called low E coatings, which are done on the wall, that is low emissive coating. Mainly reflective coating has been done for the second case, and the third, the same wall, an additional shading system was added to the first case, that is the absorptivity remains, there is no reflective coating, but additionally a shading system was provided, that is the wall is completely shaded. You can imagine there is a balcony present in front of the wall. So what happens in the first instance, the solar temperature, for example, in the eastern wall goes as high as 47 degrees, for a west facing wall it goes up to 51 degrees. This is in a tropical warm humid climate, it goes as high as 51 degrees in a west facing wall, whereas when you paint it with a reflective coating, it can be brought as low as 41 degree. You will find 10 degree difference on the external surface or solar temperature. Instead of reflective coating, if you go for a proper shaded west facing wall, you can bring it down to as low as 37 degree. You have to notice that this is more or less equivalent to a north facing wall. Imagine you have a balcony which has a west facing wall, you cannot avoid it. The better solution in today's context would be, if you are in a design stage, you can provide a balcony or a deep overhang so as to shade the complete wall. It becomes more or less equivalent to a north facing wall. Forgetting about the wind and other components which we are discussing, just with solar radiation this can be made equivalent to a north facing wall. Or if you further do not have choice, you have crossed the design stage, then the next best alternate would be to look for a reflective coating, but this is temporary, the coating would last for around 2 to 3 years, after which it loses its reflective property, it has to be recoated. There can be a slightly better improvement with reflective coating, but with a permanent shading system the whole solar temperature can be brought down. Let us discuss about few design implications. This particular graph, 2 things, this is again for Srinagar, this is winter solstice and this is summer solstice. This is the same solar radiation, but this is a direct solar radiation graph. I have split the whole thing, instead of drawing a square I have made a cylindrical structure which is segmented. So each of these segment represents a specific orientation. Say if you want to take just 4 cardinal orientation, east, west, north and south, you can refer watt hour per meter square, this is radians at this particular instance of time. This is during winter solstice in Srinagar, this is a southern sun. Summer solstice, this is a condition, this is for Trivandrum, the numbers get higher during winter solstice and this is during summer solstice. Even northern surfaces and north eastern surfaces get more solar radiation. One important thing which we should not forget is the use of, for example, northern windows or north lights. As you go down the Tropic of Cancer towards equator, northern surfaces start receiving solar radiation. It is not that northern surfaces are totally devoid of solar radiation. As you get closer to equator, what happens is sun starts traversing towards your northern wall as well. This is considering a lococentric theory. With sun as a moving body, you are located here, sun starts moving towards your north. If your building facade is this, you will still get solar radiation in your northern facade for at least 4 months for latitudes south of Tropic of Cancer. Further you go towards equator, it gets more, especially on equator there will be equal distribution, half of the year sun will be to the northern side, half of the year sun will be to the southern side. To get a better understanding, we have this graph. The small box rectangle here represents a building's orientation. These lines here, the red one indicates the solar radiation during summer, which is depicted as overheated period. The blue one, which is shown here, this indicates the solar radiation during the underheated period or the winter season. This is an interesting graph which shows that which is a major or direction from which higher solar intensity comes during summer, this is during winter, and the green one is an annual average. Typically it is understood and agreed upon that your longer surface of the building, longer facades of the building should not be facing east and west without enough solar protection. So it is a better idea to orient it, the longer surface to orient it towards north and south, shorter towards east and west. It is understood, but still you can go for minor directional changes depending on the location. For example, in case of Srinagar, the major solar incidence during summer occurs in this direction, not exactly in the east, but it occurs slightly away from the east, and during winters it is not directly on the south, but it is towards little bit towards east. It is not southeast but slightly ahead of east. So in this case the actual right orientation of the building will be a slight tilt rather than just on the plane. Consider the case of Trivandrum, the case changes. The maximum solar radiation intensity during summer occurs at 70 degrees. So this is where you get maximum solar radiation during summer, and during winter you get somewhere around 160 degrees. This is where the maximum occurs. So a trade off, the best orientation would not be just south, the longer facing, not just facing south, but it is somewhere around 160 degrees. That is a perpendicular. If you draw, this should be facing 160 degrees. This is where this would be the best case in which the building can be oriented. We will close this session here. Take a quick recap. We studied 5 important things. First thing is the earth sun relationship, how it moves around. We studied about northern solstice, equinox and southern solstice, the earth's tilt. Then we talked about how this earth movement, rather sun movement, would be translated into diagrams for quick reference, that is sun path diagrams, the stereographic projection, how it is built and how it can be used. Number 3, we talked about the effect of longitude and time zones. We calculated solar time and local time. Then we talked about the impact of solar radiation. We took specific example of a building facade and we were studying it for 2 different locations, geolocations. Then we studied about the design implications, that is how to orient your building considering the solar radiation before positioning a building itself. Thank you.